This question asks us to determine the net ionic equation and how a different reducing agent influences the EMF. We are told the cell is a galvanic cell. In a galvanic cell, a spontaneous redox reaction occurs, and this generates electrical current in the wire. A galvanic cell always has two half cells, which are usually separated by a salt bridge. We are given the cell notation here. In cell notation, the double line represents the salt bridge, and on either side is information about the two half cells. The information written to the left of the double line is the information for the anode and the anode electrolyte. The information to the right is for the cathode electrolyte and the cathode. So on our diagram, we can label the anode as lead. Its electrolyte contains lead 2+ ions. The cathode is platinum, and its electrolyte is a mixture of iron 2+ ions and iron 3+ ions. Oxidation occurs at the anode and reduction at the cathode. During oxidation, the lead metal of the anode loses electrons to the wire, and these travel to the cathode. At the same time, the lead electrode loses lead 2+ ions into the solution. Specifically, 2 electrons are lost for every lead 2+ ion which goes into solution, and so this is the oxidation half reaction. During reduction, iron 3+ ions each gain an electron from the cathode and form iron 2+ ions in solution. So no plating or deposition of iron occurs onto the cathode. Rather, the platinum electrode merely supplies electrons to the ions in solution, reducing them from 3+ ions to 2+ ions. This is the reduction half equation. Now that we have the oxidation and reduction half equations, we can add them to get the overall redox equation. We need to cancel electrons, so we must multiply the reduction half equation by 2. Now the electrons on the left and the right can cancel since there are 2 electrons on each side. We can add what remains, and we get solid lead metal reacts with 2 iron 3+ ions to produce lead 2+ ions and 2 iron 2+ ions. This equation is balanced. The charges are balanced too. This is the net ionic equation. A net ionic equation shows only the chemical species actually involved in the reaction and which undergo a change. It does not include spectator ions. We do not know what the negatively charged spectator ions are here. Next, we are told a stronger reducing agent is used, and we need the effect on the EMF. Now the species which is oxidized is the reducing agent. So here the reducing agent is lead. And the difference in the electrode potentials of the two half cells will give a voltage reading on the voltmeter. The initial EMF is the voltage or potential difference before the reaction starts, when no current is flowing, when the circuit is open. And at this point, this voltage is at its highest, and it decreases over time when the reaction starts. The formula for the EMF is the cell potential is equal to the electrode potential of the cathode minus the electrode potential of the anode. If a stronger reducing agent is used, the electrode potential value for the cathode will be larger. This will result in a larger E cell, in other words, a larger EMF. So the effect of a stronger reducing agent on the EMF is that the EMF increases.